Yeah, let's start.
Good. Let's get started. I'm going to face the camera and the audience at the same time. Welcome everyone to a in-person hybrid kind of event. We have some lovely cookies and fruit here. I hope you at home are fueling yourselves. It's great to be here for a mathematical seminar. Most of my week these days is not spent talking about mathematics, so it's really nice to be here, and I'm very looking forward to hearing more about knapsack problems. So Professor Maruyama is visiting us for one more month. Yeah, this is not his first time to Melbourne. He's been here before, and I think Moshe Schneidervich is who you were working with. Some of you may know Moshe. He taught me second year operations research a long time ago, and so you're a relatively frequent visitor to Melbourne. It's lovely to have you here, and I've been looking forward to hearing what you have to say about knapsack, because some of us have papers on knapsack, and it's an important theoretical problem, and also with lots of great applications. So Professor Maruyama is at Nagasaki University, and yeah, please make him feel welcome.
Is it working? No, we've knocked something out.
Sorry.
Share the screen. Yes.
You can see that video voice.
Oh no.
Location my cable device. You want to pass like one chain?
The cable, maybe the cables come out a little bit.
Like pass one along, and I get another one if you want.
It was working.
Sorry.
That's okay.
Let's go to the
Is your computer turned off?
Oh, you drove, did you?
Not working now.
Yeah, I've done that drive.
Okay.
Click share screen again.
At least.
No.
There you go.
Yeah,
just
sorry.
I'm
sorry.
You might just have to project your voice a little
Yeah,
bit.
do a mount.
Yeah.
And then
Okay.
you get to the
Sorry. I appreciate having this opportunity to talk in Optimat seminar. Thank you so much. So today I'd like to talk about the knapsack problem as non-deterministic sequential decision process and two types of solution methods. So first, I introduce in order to introduce the non-deterministic sequential decision process, shortly nd-sdp. So let's consider the non-deterministic shortest path problem. So this is a simple problem, namely the objective is to find the optimal path from the destination node 1 to the initial node 1 to the destination node 3. So but in this problem, we three types of times are associated, namely by bus and subway and train. So if people consider this problem, for each bus 1 to 3, the three types of times, namely T1 to B plus T to 3B, and for each path, the times by bus and times by subway and time of train, then one have to consider this problem as a multi-objective shortest path problem. But our problem is different from the multi-objective shortest path problem. So let's consider that we assume that there are some scenarios. For example, when one takes a path 1 to 3, then he does not use the same mode of transition. So this is just one example. So so S of X is a set of scenario, BS, BT, SP, and so on. So let's denote the sequence of index. We define the sequence of index like this. This means that reach the station 2 by bus and reach 3 by subway. So we can formulate a non-deterministic shortest path problem by the 5 tuples like this. Sigma is the primitive decision. 1 to 3 means that sigma element of sigma next move to node J. So and S is a set of feasible policy, namely all paths from 1 to 3. So and A of X is a sequence of indices like this. So first element is node, denotes the node, and second element denotes the mode of transition. Okay. Then, for example, A of X equal 1 to 3 is the set of sequence of indices like this. So further, A bar of X means that the subset of A of X where the final index belong to the final set of final index like this. So so for each scenario, namely I 1 2 3, many elements. We have many elements. So for each scenario, we have Fix, the length of path is like this for each path. Then first we obtain the maximum of Fi of X, namely maximize of these values. Then 5. Okay. And so we consider this value of F of X, the value of F of X. So then our objective is to find the F of X, minimize of F of X. Sorry, this notation is minimize 5 or 5.3. Then minimize of these values is equal to 5. So this is the solution of this problem. So the non-deterministic problem is also a non-deterministic shortest path problem. Is also formulated as non-deterministic SDP, namely finite automaton with objective function like this, and where each circle means that the state, and arrow. So according to each arrow, so this finite automaton to the next state. So in this 2 means that the one move to the node 2, then the 3 states occurs. So like this. So Q and QF is defined by this, but I will talk about the detail later on. So like this, the knapsack problem is also formulated as this non-deterministic finite automaton with objective function. So this talk is consisting of these 5 parts. So first, talk about the 3 knapsack problem. So this is a usual 3 knapsack problem. namely, we consider undirected tree T rooted at node 0. So, and where V is a set of nodes, which means n item. And for each item I, integer Ci, namely profit, and positive integer Di, demand or weight are associated for each node, for each item. And large H is knapsack capacity. Then the objective is to find a subtree T prime of T rooted at node 0. Okay. So satisfying such that the total profit on the subtree is maximized, satisfying that the total weight is less than or equal to capacity, like this. So this is a tree knapsack problem. And where let's introduce the variable Wj. If j belong to the subtree, then the value is equal to 1. And if otherwise, the value is equal to 0. So then the tree knapsack problem can be formulated as the following integer problem. So where Pj is a predecessor node of j, so then this tree constraint, there exists this tree constraint. So without select Pj, we can select the item j. This constraint means that like this. So if this inequality constraint, without this constraint, then we have usual 0-1 integer, 0-1 knapsack problem like this. Okay. So in the tree knapsack problem, we consider this in general this tree knapsack problem. So there are many or a few applications of tree knapsack problems. For example, single machine schedule problem or network design problems in telecommunication systems and local access telecommunication networks. And recently, Iceland partition of distribution network, and so on. So, but in this talk, we consider the other knapsack problem, namely non-deterministic tree knapsack problem. So, so let's consider this problem where two kinds of profit for each item are associated. That is, a person can select one of two different color articles or two options. We have two options for each item with the same weight, D1, D0, D2. Well, further, the person is particular about color of articles. For example, this is the root is a backpack itself. So if he selects the black backpack, then he or she select the black pillow or green pillow, and black sleeping bag or black green sleeping bag. But if he selects the green backpack, he or she only green pillow or sleeping bag, green only sleeping bag, like this. Like let's consider this problem. So we can assume we can assume that there are some scenario or restriction with respect to selection. So then, for example, this this sequence means that the article number and 100 means that the item 1 selected, but item 2 and 3 not selected. So then this is 1, and 1, 2 is the article number, black or green. So 1, nothing. And so for each selection of item, so a few, 2 or 3 in this problem, 2 or 3 states, there exist 2 or 3 states. So then we can formulate this problem like this integer programming problem. So this is the same as the usual tree knapsack problem, but this is first minimize of this sequence. After that, we consider maximize. So max mini problem. We consider the max mini problem like this. So this problem is complex in the minimization. So okay. So this is so I can know the solution method for this problem directly. So I have represent this problem like the non-deterministic discrete decision process like this. So this DDP is consisting of 5 tuples like this, where sigma is a set of primitive decisions, and sigma star is a set of all strings policies composed of primitive decision, and epsilon stands for the null string, and S is a set of feasible strings or policies, and F is a profit function, which our objective is to find and maximize the profit function. So where fx is minimized of fi of x. So we consider the non-deterministic tree knapsack problem like this. This is.
Can I just ask,
okay.
why is it non-deterministic? Or what is, where is stochastic?
Not
It's
stochastic.
in the W?
Yeah.
W is
Yeah.
stochastic,
Not stochastic.
non-deterministic.
Non-deterministic. But I use the term, so non-deterministic finite automaton. If we use the non-deterministic. So if decide the selection by select one, if we take one policy, then few states, then the automaton is called as
Yes,
non-deterministic.
the search is non-deterministic,
Yeah.
not the data.
Yeah,
It's
yeah.
stochastic data.
Yes.
Okay.
Yes.
Thank you.
So then we consider this problem, and this is a color for this is a profit for each color. So and 182 is a weight, and this is a scenario like this. Then the non-deterministic tree knapsack problem as non-deterministic DDP like this. So primitive decision 0, 1, 2, 1 bar, 2 bar. 1 or 2 means that the select the item 1 and select the item 2. 1 bar means that not select. 2 bar is also not select. And then the feasible set is S is like this. So because 0, 1, 2, if we take 0, 1, 2, so the capacity is over. So this is nothing, 0, 1, 2. And a set of scenario like this, then the set of indices is like this. So this is, so according to these indices, sequence of indices, the objective function fi is calculated like this. Then f of x is minimum of these values, 14 and 16 and 15, minimize of these values, then 14. So in the same way, in other strategies, we can calculate f of x like this. Then finally, we want to find the maximum value of these, then 14. This is optimal, maximally the value. So, so in general, for this type of problem, we can show that the non-deterministic tree knapsack problem as non-deterministic DDP, like this. I omitted the detail, like this. So Maruyama obtained the necessary and sufficient condition for the non-deterministic discretization process to be represented by non-deterministic finite automaton with objective function. Anyway, that problem can be represented by non-deterministic finite automaton. So non-deterministic finite automaton means that this is the state. For this state, the action or policy A, then two states. There exist two states, or 3 or 4, a few states. Then this arrow means that the state transition function. So QF is a set of finite states. So the objective function is defined like this. For the state Q, and in the state Q have the value xi. After taking a policy A, then for the next state, the objective function, the value of objective function is like this. So, and successively, we can define the value of objective function like this. So then H, so this is YQ0X, it means that the sequence of states, the set of sequence of states from the initial state Q0. This is the sequence of states. So then on the set of sequence of states, the first we minimize of h bar of x, and second h bar, and next stage we maximize the function h bar of x, namely max mini problem. So the non-deterministic sequential process have some types of subclasses like this. This is the monotone sequential process, namely with respect non-decreasing with respect to xi. Then this process is called MSDP. And if strictly inequality holds, then we call this non-deterministic SMSDP. Further, monotone sequential process satisfy this inequality, then this is a non-deterministic PMSDP. So, for example, in shortest path problem, this is a class solved by Ford method or power method. And this, so for this class, the Dijkstra methods are applied. So finally, this is a loop-free monotone SDP, namely the finite set. This policy set is the finite. Then we call this loop-free monotone SDP. So the knapsack problem is belonging to this problem, this class. So anyway, if the h bar q0x equal, this is a f equal the discrete decision process, the objective function of discrete decision process. H bar x equal finite objective function, the value of objective function in automaton. Then both value is same. Then we call the strongly representation. So the representation is several type of representation. If the h bar q0 equal fx, then super strongly representation, and h bar x equal fx, then we call strongly representation. And if the optimal solution is the same, then we call weakly representation. So we concentrate on the super strongly representation in this talk. So sorry, back to the knapsack problem. The knapsack problem as non-deterministic loop-free MSDP like this. So the Q is a state, and Q0 is an initial state, and QF is a final state. The state Q is first element is the sum of weight, and second part is L is a node, and M is the article number, and J is the article number in root node, and K is a stage. Like this, the state is defined like this. And the state transition is also like this. Then the objective function, then the cost function in non-deterministic nd-msdp like this. Namely, next, this is the stage K, and the next stage is K plus 1. Then if the item K plus 1 select, then the weight is added like this, D plus A K plus 1. And if they do not select K plus 1, then the weight is same. Weight is the same, not select. Like this. So in this program, Q is defined by this, and state transition is like this, and objective function is like this. And this is a finite automaton with cost function in the non-deterministic MSD for the tree knapsack program, like this. So after formulating like as a finite automaton like this, for this process we can use the one solution method, namely recursification. So let's consider this type of problem. So the total weight is 12. This is a limit. So then for this problem, for this is a recursification for the sequential decision process, non-deterministic loop-free monotone sequential decision process. this recursification holds. With this recursification, we can calculate the for each state, this recursification holds, and this recursification holds, and to tell that there are many states. But finally, the final stage is equal to 0. We put equal to 0. So then backward, we can solve this problem. So backward, we can this problem. The optimal solution is 49. This is the optimal solution. So namely, this is the first tree, and the red line is the optimal subtree, and the value is 49. And okay. Then, but for this solution method, we have to many state calculation. So we consider the next solution method. So in order to apply the depth-first dynamic programming algorithm, we introduce the new variables x1 to x2i for each articles. Then this program, the objective function is rewritten by this, where ux is xik is less than or equal to xik or xjl, and large X is values for each node, satisfying this equality. And mu is a set function of values, and each value is defined by this. Then the constraint, tree constraint, and scenario constraint it disappear, and the objective function is written like this. So this is a Belyakov form. This is very convenient form. So by using this form, in this form, the large G prime, small G prime is defined by this max-min function. For this function, this recursification holds. So by using this recursifications, forward move and backward, we use the forward move and backward move on the same problem. So initialization and forward move and backward move and so on. So this is a optimal solution. We can have the same optimal solution. And this is a item 0, the article 1 is select. Item 1 and the article 2 select, and so on. We can find the solution like this. So this is a depth first dynamic program algorithm, namely 1, 2, and forward move, and backward move, and forward move, and backward move, forward and backward, and so on. This is using this method, we can solve this problem. So next, finally, let's consider the non-deterministic knapsack problem as nd-sdp. The following knapsack problem is have no structure, no tree structure. So let's begin with the max mini zero knapsack problem suggested by GU. This is a alright. Given a set S of scenarios. So for each item, integer CIS, profit of item I, and a scenario S. So objective is to find a X where xi equals 0 or 1. And so with respect to the scenario, we calculate the minimize. So after that, we maximize subject to the weight condition. So this is a integer programming problem like this. So this is the max mini and knapsack problem. Okay. But in this, for example, this is a 1, 2, 3 is the item number, and DI is the weight for each weight, and CIF is the person F for item I, and the profit is 3, and for 2, and the profit is 7, and so on. CIM is a person M, and 5 for 2. Then, for example, x1, 2, 3, then 1, 0, 0 name that the item 1 is selected, 2, 3 does not select. Then the total weight is 3, and F, person F, the total profit is 3, and then for person N, the total profit is equal to 5, like this. But this case and this case is overweight. Sorry. Now, capacity is defined as 8. Then two cases is overweight, but the other case less than or equal to 8 weight. But the profit for each person weight is like this. So max mini problem is the minimum. So two numbers. First, we find the minimum 3, 7, 4, 2, 6. This is the minimum. So after that, we find the maximum. Namely, this is the solution 7. Namely 1 or 1. So if we select item A1 and item 3, then the optimal solution, we get the optimal solution. And in non-deterministic case for this problem, so for example, 2 persons, if 2 persons, 2 persons will decide to pack or not to pack each item or knapsack by item turn. And for each item I, 2 kinds of costs, CIF and CIM, are associated respectively, according to each person's liking. And further, let us draw up the following rule. So if he or she select nothing, then the next item turn, female's liking article or a person's M's liking article can be selected, or nothing. But if this time the article for the which is adequate to the person F's liking, then next stage do not select or the other person's liking. So they can select. They have to select the other person's liking article. So the other case is also If males liking, then nothing or males liking. Then this is 1, 2, 3. Then this is item 1 selected, and the other items does not selected. Then this is a few, only one, not only one, but few. There exist a few scenarios like this. Then according to this, the object function, the value is like this. For example, x1 is selected, but 2, 3 is does not selected. Then these values, these values. Then minimize 3, 5, 4, 2, 8 like this. So okay. Then the solution is 8. Okay. Then, but in this problem, it's complicated because if we change the select order, so the before case, first one, and next two, and finally the item 3. Then this is the value, optimal value. But if we change the selecting order, if 1, 3, 2, then same. In this case, the same optimal value is same. But if we consider the item order first 2, second 1, third 1, 3, number 3 item, then the optimal value is changed, namely this one. So in this program, this is same, but this is that's change. So this is the same and this. So we have to consider the non-deterministic knapsack problem with no tree structure. We have to consider this value. Further, we consider the order of selection. So further maximize with respect to the order. So like this in this part. But this problem is also nd-ddp or like this, and this problem also non-deterministic loop-free MSDP like this, where the state is different from the tree knapsack problem, but we can formulate it as the nd-msdp like this. So this is a state transition, and this is a objective function after the policy L. Then this is a new state, and if he does not select L, then this is the next state. So like this. For this problem, this is a finite automaton, where the first we select one not select. Then this is a part of the first two and not select 2, and this is a 3 and not select 3. So, but for each order, we can use this recursification. We can obtain the objective function. For example, 312 over h bar of 312 over is equal to 5, and 31 bar 2 equal 6. Then after that, we can calculate the maximize of h bar of x. But this is not good. So I'm looking for the efficient algorithm. So that are not solved. Sorry. So anyway, in this talk, strong representation for the non-deterministic tree knapsack problem by nd-sdp, and two types of solution method by dynamic programming. So strong representation for the non-deterministic knapsack problem by non-deterministic sequential process. So future study, I do hope that the practical application of non-deterministic tree knapsack problem or non-deterministic knapsack problem, and solution method for tree knapsack problem by branch and bound method or meta-heuristics. So it's famous for the three methods: dynamic programming, and branch and bound, and meta-heuristics for knapsack problem. So further solution method for non-deterministic knapsack problem without tree structure by dynamic programming, by branch and bound method or meta-heuristics, and so on. Anyway, I'm looking for the practical application of this. So sorry, I stopped my talk.
Okay, thank you so much. Do you have any questions for Professor Maruyama?